Thank you, everyone, for coming out here. It's bright and early, and it's very nice to see you all here. I hope I'm not too boring. Stop me at any point if you have questions. I'm Alex Spangher, as the wonderful MC introduced. I work at the New York Times until this time next week, when I will be leaving for Microsoft Research. But as long as I'm at the New York Times, feel free to ask me any questions about news. Because I'm from the New York Times, we're going to start with the homepage. So when we look at the homepage, you know, in any given day, we just approach it as casual readers. We notice a lot of stories here that are sort of jarring. We have some political violence stories, some migrant stories, some contentious bills being passed. The story gets, you know, only worse as we dive into the section fronts. We have, you know, Russian diplomats, Russian craziness, some more political violence, some refugees. In short, you know, is anyone feeling a bit tired these days? Like that guy? It's going to be a tough news environment. What if we could predict the effect that our articles would have on people? We might be able to build new and interesting products. So we could recommend articles that might make people feel a certain way. We could have a better understanding of our readers. So we could understand when readers are about to subscribe or when they're about to not subscribe. Let's say you read a bunch of sad articles and then you unsubscribe. We could start to craft an understanding around that. And at the end of the day, we could start to try to become better web citizens. So we can try to not overwhelm people with what's going on and tailor the news such that people get the maximal information without becoming overwhelmed. So there's a lot of things that we can do if we had this understanding. Hence, the attempt to get this understanding. Project Fields. That's me. I'm Alex. This is my boss, Dr. Chris Wiggins. Project Fields was valiantly prototyped by an intern, Sue Hong, in summer of 2017. And so, thank you to her. So, the gist of Project Fields, and what we'll be talking about here, is, of course, how can we predict the emotional impact of articles on our readers? But to do that, we had to collect a lot of data that was new and interesting. We had to train models to model this data, and then we had to deploy those models. So I'll go through each of these as several broad topics, and please feel free to stop me at any point. But without further ado, I'm going to turn over my presentation to Harry Shearer, who is the principal voice actor for Principal Skinner on The Simpsons.
This tool, don't you like tools? Don't be one. The one tool was based on an initiative called, and this is why I'm sharing this with you, just so you know that the New York Times uses this kind of lingo when talking to advertisers. Project Fields. Project Fields. Project Fields. Project Fields. Just have to keep repeating that. The Times is already, not Project Feelings, Project Fields. The Times is...
Okay, thanks, Harry. That was sort of a life mission for me to get Principal Skinner to get completely baffled over my naming choices. So you know that when 90s voice actors get confused, that something is going right. But in this talk, I'm going to break it down into 6 parts. I'm going to talk about the data collection, the exploratory analysis. So what does this data say? Some modeling approaches that we took, offline testing, online testing, and then production. And yes, data is a plural word, all you data scientists. This was something that I had to have taught to me by journalists. Datum is a singular. Okay, so normally as a data scientist, when you want to study something, you usually try to find the closest proxy. So if you want to study attention or willingness to subscribe, you try to get a proxy that might be time spent or return visits, a metric that you can observe that it gets you halfway there. Unfortunately, there's not much of a proxy for emotions. So what we did was we actually got exactly what we wanted. So we used crowdsourcing. And if you've never used crowdsourcing before, crowdsourcing is this amazing experience because you can customize exactly what you want to ask people. You can collect the exact data that you want to collect. You can do it really, really quickly. You can do it repeatably, at scale, and you can It doesn't even really cost that much if you design the right task. So there's something magical about crowdsourcing. This was sort of my first experience with it. And if you haven't tried it, I really recommend you do. But we used Amazon Mechanical Turk. And these are the tasks that we constructed. So when you're doing MTurk, you construct these tasks. And workers come to the MTurk site and they see these tasks and they fill out whatever your questionnaire is, and then you'll get that data the next day. Or, whenever you pull it. But we showed our workers the headline, summary, and the thumbnail image, because the emotional content of an article tends to be packed into those upfront things to hook the reader. So that was sort of all they needed to see. We did this for 20,000 articles. Each article we asked 10 different workers to tag. So that gave us a total of over 200,000 results. We had 6 rounds of tagging. The first was random, and the next were active learning or active sampling. And I'll go into that later. Active sampling is really cool, but we'll go into that later. So that's sort of a broad overview of the data that we collected. This is what it looked like. So you have each one of your URLs is replicated 10 times, and for each URL you have a vector of either ones or zeros for if that person felt that or not. So each one of these is an individual worker. So for this Bob Corker article, we had, this person felt interested, this person felt really, really sad, and this person felt hateful. Oh no. We had over 1,200 workers complete our surveys. Many of them completed over hundreds of them. We did put some caps on there so that people couldn't just run through and do thousands of them because, with spammers, you tend to get people that run really, really quickly through your tasks. And they earn a lot of money, but they give you garbage data. So there's some caps that we put on there. Our workers were great. Who were our workers? Our workers gave us some really great feedback. They reached out to us. Engaging with actual people is also great because you can get this sort of feedback. This person told us, maybe you should add a little bit more emotions to your data set. And that was some cool feedback. This person was also great. She sent us a picture where she lived. And she gave us some more feedback. Maybe we should include the WTF emotion. I'll keep that in mind, Renee. This person was also great. They gave us feedback as well. And this made a nice little round trip with the lawyers. But MTurk, people tend to be paid around $4 to $5 an hour. We did not know how to price our tasks in the beginning, so we ended up paying despicable slave wages. But at the end of the day, we repriced it so that based on the median time, we were paying about $8 an hour. But who were these people quantitatively? What can we say about this entire population? We asked them 2 questions. So how often do you read the New York Times, and what is your zip code? We didn't want to ask more than 2 questions, and this is something to keep in mind if you're ever going to do crowdsourcing. The more questions you ask users about themselves, the more you prime them to give specific responses. So if I start asking you, hey, what's your age? Are you married? Where do you live? What's your sexuality? What's your XYZ? The more questions I ask you, the more I bias the responses that you're going to give me. So if you're trying to collect a ground truth data set, you want to include as few questions as possible. And these 2 questions are pretty good questions because they give us a sense of how much the person interacts with the product, and they also give us this join code. So zip code you can join on a lot of different data. You can join on county level voting data, exit polls, census data, what's the proportion of males and females in that district, what's the proportion of races. So you can get a lot of information about people just through a zip code. These are where our workers reported to live. That's a nice healthy distribution of a lot of the estates that Hillary Clinton lost. They're also a lot more dispersed than our readers. Our readers tend to be coastal. So this gave us a nice healthy population in the United States. We have reason to believe that this is correct, like this is truthful results, because a lot of studies have shown that Turkers, a lot of people think that these workers are like, low-paid workers in some country that's not the United States, just like clicking through results. Actually, a lot of independent research shows that Turkers are US-based grad students, which is really fun.
Did you also check for IP numbers, stuff like that, so they're not so just far away?
Did we also check on IP numbers? Amazon doesn't report on that unless you pay them extra money. But as we'll see later, these data sort of make sense. Yes, I mean, definitely we would ideally want to do extra validation, and we probably will do extra validation in other realms. There's also statistical techniques to cut out spammers, and if I have time, I can get into those. So that's sort of a post-analysis cleanup that you can do, which is actually really helpful and boosts our accuracy a lot. So these are where the people lived. This is how much they interacted with our product. So over 80% of them interacted more than one time a month, which was great. Less than 10% have not read the New York Times at all. So we feel confident in our workers here. And if you're ever going to do crowdsourcing, it's good to ask a couple of questions to make sure you're not completely off base. Now let me jump into active learning. Active learning is really, really awesome. The problem statement in active learning is that you have a lot of unlabeled data. Like you have a lot of articles that are not labeled, and it's cost restrictive to label them. So you want to select, you can only label 100 or 200 data points. So you want to select those 100 data points that'll give you the most information about your problem. So you want to select the best 100 data points. To explain what I mean about what are the best 100 data points, let's consider this article. Does this article cause hate? Yeah, I would say it's pretty clear that this article causes hate. You guys agree with me? It has graft and corruption, and that's a hateful article. What about this one? Does this cause hate? I see some nodding heads, which is, I think this is a pretty clear choice for one that doesn't have hate. It has the word dog in the title, which, what about this one? Right? A little bit more confusing. Recent political statements have changed Kanye. I don't know Kanye. But his music is great. So, sort of 50-50 here. So this article will give us the most information about our problem because it's confusing. It's a confusing article. So if we can get the ground truth on this article, we can build a better model. And that's the idea with active learning. You'll build a simple model, and this simple model will help you identify in your pool of unlabeled data, it'll identify the most difficult articles, and then those are the articles that you're going to ask your human annotator or your oracle to label. And then you'll get that ground truth set, you'll retrain your model, and you'll do this iteratively, so you're continually identifying the hardest articles. This raises the question, what do I mean by hard? What is a difficult article? There's a lot of ways to define difficulty. You can look at the articles that you're most likely to get wrong. You can look at the articles that you're most likely to disagree on. We chose a definition of difficulty that is known as a priori expectation. So, to understand this, let's return to the Kanye article. Let's say that I ask you as the model, because you guys are all supermodels here. Let's say I ask you, how likely is this article to cause hate or fear? And you read the headline, you have no idea. You're like, I'm super confused. I don't know, Kanye, what do I do? However, you do know that about 50% of the articles in our data set cause fear. You would be pretty safe in saying, oh, this article is 50% likely to cause fear. And that's exactly what we're doing here. We are looking at the articles. So our model is predicting this is the distribution over scores. And this is the mean of the scores. And we're taking the articles around this mean, and we're saying that those are the most difficult articles to classify. How are we able to make that assumption? Well, this equation tells us, the right side of the equation tells us the a priori expectation. So this is the expectation of the fear in the article before we observe the input data. And if that is the same as the expectation after we observe the input data, that means that the input data did not add measurable signal to our problem. So we look at the headline and summary, and we still have no clue. Our guess doesn't change. And so that means it's a difficult article. And so if we do that multiple times, we keep on updating our definition of difficult, we find that we produce a data set that actually trains smarter models than a randomly selected data set. Yeah? No. No. Because you'll see later, we could have like a situation where 10% of the articles get tagged with an emotion. So it's whatever the mean of that emotion in the population is. The population of articles. So And we tested this on the same random set. So this is on a different holdout set. We found higher accuracy with our active models. And so that wraps up the data collection part of this talk. Is there any questions about the data collection? So you, this part of it? Okay. So when you have a model that scores a data point and says that this data point is a 1 or a 0, your model will predict this data point is 90% likely to be a 1 or 10% likely to be a 1. Before even observing the data point, the model can say, oh, this data point is 10% likely to be a 1 if it knows that 10% of the data set is a 1. So that's the a priori expectation. A priori means before observing. So it's like I ask you, I'm going to flip a coin. What's the likelihood that it's going to be a heads? You can say, oh, a 50% likelihood. That's your a priori expectation. Now you observe a lot of coin tosses and you see head pop up a bunch of times. That would be your input data. That would be X. Let's say you see heads pop up on that coin like 90 times out of 100. Then your guess for the next coin toss would be a 90%. So that is a situation where your a posteriori expectation is different from your a priori expectation. Now, let's imagine that it's a very difficult coin to observe, and you don't know what a head or a tail is. You can't tell anything about the coin. Even if you observe a bunch of coin tosses, you observe me flip that coin like a million times, but you can't tell much about whether it's a head or a tails, then that input data, that X, doesn't change your expectation. Your expectation is still what it was before because the data is difficult to understand. So that's our signal that the data is difficult. When it doesn't change, that means that the data is difficult. And that's the articles that we know we need to ask more questions about. Yeah?
Did you see any differences across geography on how people rated scores of emotion? Because I'm just wondering if you're getting a lot from a certain part of the country, if that would sort of bias the sample, if you're getting more from, more emotions from this part of the country on these kinds of articles, more emotions from this part of the country on these particular ones.
Yeah, totally. So the question was whether there are metadata that impacts the distribution of motions that were tagged. So like geography, whether people from a different part of the country are more likely to tag an article in a different way. And that's a really great question and definitely one that we want to look at. That would probably involve a lot of hierarchical modeling. So we would probably have to do modeling in 2 stages, which is awesome. This is totally on the roadmap and something we want to look at. But that's a great question because so we'll look a little bit about polarization, and I'm sure geography informs polarization. Any more questions? Yeah. AUC. So yes. So AUC, which stands for area under curve, is a great metric to use when you have a very unbalanced data set. So if your data set is 1s and 0s and you have like only 10% 1s or whatever, AUC is a great metric to use. Okay, so now let's talk about exploratory analysis. As data scientists, as soon as you collect a data set, the first thing you want to do is poke around and make sure it looks sane, make sure that there's no bugs in the way you collected your data. So the first thing we can do is look at what are the top articles for a certain emotion. And this is an audience participation part. So this is the top article in one emotion. What do you guys think it is? Is it hate? Is it sadness? Any guesses?
Fear.
Good job. Yeah, you guys got it. It's fear. How about this one? Oh, look at those privileged people. What do you guys think it is? Yeah, it's love. Good job, guys. How about this one? So we got some hope, we got some fear, we got some happiness. It actually is happiness. But this is an interesting point because it brings up a sense of polarization. Some of us might be scared by this. Some of us might be hateful. I don't know. So we can look at polarization. And polarization is a situation where you have a strong negative correlation between two opposite emotions. So this would be a good example of an article that causes polarization. You can see that in the love and the hate column, workers are either going to rate love or they're going to rate hate. They're not going to do both. And they're not going to do neither. So we can look at the articles that pop up the most for this negative correlation. So for happiness and sadness, I mean, this makes sense. Maybe there's people that want to see this White House fail, and there's other people that are sad when the White House, or I don't know. Or maybe there's, for news media, maybe there's some people that just hate ESPN. Not saying that as a New York Times employee I hate ESPN, I'm just saying maybe there's people that do. For boredom and interest, I mean, for a lot of us here, maybe artificial intelligence and the regulation of that is a very interesting topic. For other people, maybe it's a boring topic. This one sort of confuses me down here, this London Zoo fire. I don't know why that would cause hope, unless maybe people are hopeful that the meerkats are escaping and living a better life somewhere in London. So that's the negative correlation within an article. We can also look at the correlations overall. So which emotions are correlated with each other. And this is logical. The output of this largely makes sense. I mean, we can see that the positive emotions down here, happiness, hope, and love, are all sort of correlated with each other. Whereas the negative emotions, fear, hate, and sadness, are also correlated with each other pretty strongly. Boredom is not correlated with any emotions, which also makes sense. And then, to get at someone's question, we can look at how likely an article is to be tagged with a certain emotion. This also makes sense. So, interest was like about 40% likely to be tagged, which makes sense. An article can be interesting for a lot of different reasons. Whereas articles were less than 4% likely to cause love. Love tends to be either wedding articles or articles about New York, which is odd. Okay, so that wraps up our exploratory analysis. Any questions? Yeah.
When you presented to the Turkers, did you present it so like headlines the same size as they were in the paper, or uniform across all articles?
That's a really good question. It was uniform because, as I'm sure you know, there's a lot of variation in the way articles are presented in the paper. We had discussions about that. We wanted to keep things as constant as possible. We even thought about using New York Times font, but we decided not to do that because we wanted to keep it more general and abstract. But that's a good question. Maybe we can experiment with that later. How what? How do we evaluate whether crowdsourced label was wrong or right? If I get to the appendix, I can show you some of the Spangher modeling. And Spangher modeling is really cool because you're looking at how likely a worker is to agree with the rest of the workers in different ways. Because there could be some legitimate areas of disagreement, like this polarization where you're either hateful or loveful. If you just the whole time you just rate yourself as angry or something, you're either like an angry mom or you're a spammer. That was a joke about the mom. So that was part of what we did to clean up our data source. There's also other things you can do. You can look at the people that complete tasks under 1/10 of a second. There's a bunch of those. Those are definitely spammers or very quick emotion people. Yeah, that's a great question, and that's actually where we started this project. We thought we were going to look at Facebook reactions, but as we started talking more to our editors, we realized that the set of emotions that they are most interested in for news tends to be a bit different from what Facebook is most interested in. Also, I think there's a strong order bias for the way Facebook collects their reactions because they always show like first, followed by the next 5, which are in order, and that creates a lot of bias in your data set. we were randomizing the order of our emotions to try to eliminate that bias. But the real answer is that we wanted to collect more specific emotions rather than the 6 that Facebook provides. Yeah.
Are you able to randomize the sequence of emotions? Are you able to look and see if it was multiplicating on the first endpoint?
That's a great question. The way the page was rendered was client-side, so we weren't collecting information about what the order was. That's a great question, but the randomization would have eliminated that effect. Yeah. There's a hand back there. Yeah. That's a good question. The question was whether there is a sort of whether interest is not a specific enough emotion, and whether it's just like too prevalent to really be distinctive. That's a good question. I'm not sure we looked at that. I'm also not sure that. I mean, it is a lot more prevalent than the rest of the emotions, but it's still less than half. But yeah, that is a good question. And we can definitely look at that later. Yeah, you had a follow-up. Disagreement between workers? Or? I mean, we saw disagreement on the article level, definitely, which was the polarization that I showed. We saw workers disagree with each other, which was part of the Spangher analysis that we did. I'm not quite sure what else you're referring to, but maybe we can talk about that after. Okay, so unless there's any other questions, I'm going to talk about modeling, which I assume is of great interest to a data science conference. So for modeling, we tried 10 different approaches. One of them was a linear approach. Then we tried 2 ensemble approaches, and we had 7 deep learning approaches, which is all cool and fancy. And I get to say deep in this talk, which apparently draws a lot of hype. But linear methods are a great place to start whenever you're doing modeling. So a linear method might be like a logistic regression, a support vector mechanism, or a linear regression. Linear methods are great because they're very simple and they're interpretable. So this level of interpretability really allows you to baseline pretty well. It allows you to understand your data set well and assess the signal that you sort of expect will be there, because you can peer inside the black box. So it's great for performing intermediate tasks like active learning. So all the modeling we did for the object learning section was all linear modeling. Linear modeling is able to do this stuff because it makes very strong assumptions about your data. A linear model assumes that none of the features in your data interact with any other features. It assumes that, feature 1 is independent, and whatever the value of feature 1 is, that's going to be reflected into the output. Also, there's a linear effect. So if feature 1 is 10, that creates 10 times more effect than if feature 1 is just 1. And so these are pretty strong assumptions about the data. What was our input? So we showed them headline, summary, image. For all of these tasks, all we looked at was text. So I'm a text person. I have not yet dove into computer vision. But so for all of these tasks, we're looking at text. For linear models, the best way to represent text in terms of an input feature is word counts or bag of words. So a bag of words is actually a mathematical concept, which I just learned. I thought it was just a fun phrase, but you guys are probably more familiar with a set. A set refers to a grouping of items whereby each item is represented only once. A bag is a grouping of items where each item is also reflected next to the count of times it appeared in the observable set. So an example of a bag of words for the headline, Trump tweets and then he walks around and then he tweets again, would have the word Trump once, it would have the word tweets twice, it would have the word sleeps 0, because he doesn't sleep. Also because your entire vocabulary is represented in each input vector. So it's either a 1 or a 0, or a 0 or a 2 or 3 or whatever. for the amount of times it occurred. And so you can notice that order has no effect here. So the order that the words appear in a sentence are not reflected in the input vector. That's also losing a lot of signal. But at the end of the day, it allows us to interpret. So we can look at which words are most likely to cause boredom, or which words are most likely to cause fear. Clearly, there's not a lot of sports lovers here. These interest words sort of confirm what we were saying earlier, that interest happens for a lot of different reasons. You can see that there's, art and companies and science and makers. Next, we looked at ensemble methods, specifically, yeah. Mm-hmm. Oh yeah, great question. Yeah, we just looked at unigrams. We did look at bigrams and trigrams, but they decreased the accuracy, probably because they exploded the size of the feature set. So the question was, how do we encode our words? And so the sentence Trump sleeps and walks around then sleeps, or whatever, you can choose each word by itself, or you can choose word pairs, like Trump sleeps would be one, sleeps then would be a one, whatever, so you do that pairing. That will capture a sense of order. However, so that's known as a bigram representation. A unigram representation, the size of your vector would be v, and a bigram it would be v squared. So it's a lot bigger. This is probably why it underperformed. Okay, so for tree-based models are sort of the other extreme from linear models. Linear models are simple and interpretable, and they make strong assumptions about the data. Tree-based models are extremely accurate. They tend to be very black box. And they actually don't make any assumptions about the data. They say that, okay, the data, we're just going to take as a given that the data is extremely complex, and we're going to try to model it that way. And I'll get more into that. But tree-based models are a great place to start after linear models if you want to you want to see the first approach of how accurate you can get before going into custom modeling. But the reason why they're good at modeling complex data is that they assume that every feature is going to interact with every other feature, and they prepare for that scenario. They also assume that every feature is very nonlinear. I'll get more into what both of these things mean later in just a slide, so hold off. But in general, they're useful for when you assume that your problem is very complex, but you assume that you don't know anything about your data set. So you don't know how the features interact. So you want to assume that every feature can interact with every other feature. And again, we use bag of words for this. Okay, so what do I mean by interaction? Here is an example of a very simple model that captures interaction. So this is a decision tree. And what this model says is that you look at your sentence. If your sentence has the word Korea in it, then we're going to go to the left. Okay, so now we know it has Korea at least once. Does it have negotiate twice? Let's say it doesn't. Maybe it's a headline saying like Korea is about to launch a nuclear weapon, and then of course it's going to cause fear. But let's say it has negotiate a bunch of times. So the negotiators arrived in Korea to start the negotiations. Then maybe it'll cause hope. So this is an example of an interaction. Specifically, what an interaction means is when the value of one feature affects the way the value of another feature impacts the outcome. So we can see that negotiate interacts with Korea. If negotiate is present as a feature, then that affects the way Korea impacts the outcome. So compare this with a linear model where there's no interactions. If Korea is in the sentence, then it's going to cause fear. If it's not in the sentence, then it's not. It doesn't matter what else is in the sentence. So you can see that we are capturing a bit more of the complexity of language. Was there a question? Okay. Nonlinearity is a bit simpler to understand. This model just says, if the word economy is in the sentence once, then it's going to cause hope. If it's in the sentence more than once, then it's going to cause fear. So picture a sentence that says, 1,000 jobs were added to the labor market and the economy is looking very good. Economy is used once. It's a simple sentence, probably very hopeful. Now picture another sentence. The economy is doing really well, but last quarter the economy was sort of faltering, and we look at economic downturns and et cetera, et cetera. That's probably a Paul Krugman article, in which case it will cause fear. So what nonlinearity means is that the way a feature affects the outcome changes as that feature either grows or shrinks. And this makes sense. I mean, if a feature is present a lot of times, that effect is probably going to change. And a tree-based model does a great job of capturing that. Any questions about random forests, XG boosts, gradient boosting? After doing that, we turn to deep learning. Deep learning is more of a custom approach. So it shares similarities with tree-based learning, but while tree-based learning sort of assumes the worst, tree-based learning assumes that every feature can interact with every other feature, and every feature is nonlinear. Deep learning sort of finds the middle ground. So if you have knowledge about your data set, you might be able to encode some of that assumption and produce a model that has greater accuracy. For example, with text, you might know that the word that follows your word is going to interact more than a word that comes farther in the sentence. So you have this local proximity that matters. And we know that to be true with text, unless you're a bad writer and you have a lot of dangling participles. We know that sort of locality matters. The same with deep learning does really well in computer vision, because we know that there's a pixel, and the pixels around that are going to affect that pixel more than the pixels very far away. So we know that there's sort of this assumption about the interaction of our features that we can encode. And so it's useful when intuition exists about the structure of the data. This is an example of a neural network diagram. If you're not familiar with neural network diagrams, this is the input layer. So this is where your headline or your summary gets fed into it, and then this is the output. So this is where the emotion gets predicted, whether it's 10% fear or whatever. These are all your hidden layers. So these are hidden nodes within the neural network that encode information and encode different types of interactions. You can see, based on the way these arrows are drawn, that there's a sort of local effect being captured. So the word Russian feeds into this hidden node, and then the word investigation feeds into this hidden node, but this hidden node gets information from this hidden node. However, this one over here gets information from this hidden node, which is also capturing information from this one, but it's sort of diluting it. So you can see the effect of H2 on H3 is greater than the effect of H1 on H3, which is how we're able to capture this sense of locality. So the more distant a word is from Russian, the more hidden layers it has to pass through. And so that's how we're able to capture this interaction. Neural network diagrams can get a lot more complex. These are all the neural networks that we tried. This is not really meant to be interpreted, but I'll tell you that this one was the one that performed the best. Now, what can we say about these diagrams? What can we say about why that one performed the best? Well, let's look at this layer. We'll notice that all of these diagrams have an embedding layer. This is the only one that has a pre-trained embedding layer. What is an embedding layer? If you guys have read anything about Dr. Beck or anything, you're probably familiar with this diagram. But an embedding layer, more generally, is a low-level semantic space. So it's a space in which directional movement along one axis connotates some sort of semantic meaning, which is usually a very simple semantic meaning. So this is a space where movement along this axis connotates gender. So as we move from here to there, we go from man to female. This is a space where movement connotates verb tense, and here there's a geopolitical meaning. But you can see it's a very low-level information space, and it's often the best space to fix with pre-trained data. So in deep learning, you usually need a lot of data to make things work. However, you can often get advantages by taking the models learned in one context and applying them to another context. That's sort of like saying, you can come into this room knowing English, And you don't have to learn English while listening to this presentation. Hopefully, if I'm not worse than a halfway decent lecturer, you'll learn something from this presentation. However, you don't need to like come in and also learn English because your embedding space for English is already fixed. One thing that really drew me to deep learning, I studied neuroscience in undergrad, and in the human brain, there's well-studied the visual pathway where information from photons hitting your eyes is transformed into actual meaningful images. And so the way that happens is that your eyes collect data from photons, and it gets transformed in the primary visual cortex, and then it goes to the secondary visual cortex where more meaning and information is extracted. But the primary visual cortex can be thought of as a low-level embedding space because the primary visual cortex extracts edges and lines and shapes and circles or whatever before transforming that. That forms early in your life. So that's sort of fixed before you go off in your life and learn more. But I was reading this neuroscience paper once, and so when the information of edges and lines gets transformed into squares and shapes and more meaning is added onto it, finally gets to your prefrontal cortex when you can actually associate meaning and images and people and faces. And they found this one person who had one neuron that in his primary visual cortex that turned on when he saw a picture of Jennifer Aniston. So it was a Jennifer Aniston neuron. And that's pretty amazing if you think about it, because that person had to take in a very sparse data set, whether this photon excited this rod cell or this glial cell or not, and then extract lines and colors and meanings and experiences from it, and transform that information through layer and layer and layer, until finally he could say, oh, this is Jennifer Aniston. Which I find to be pretty fascinating. But clearly he didn't have to just learn that as a task. And so when we stepping back into machine learning, a lot of this has a name, it's called transfer learning. So a lot of machine translation will look at the transfer between English to another language. Okay, the screen has told me that I should stop ranting. And that concludes our modeling section. Is there any questions about that? Yeah, so for some of our networks, especially the RNNs, which is the same thing as an LSTM, the nodes sort of unwrap. So the length is equal to the number of, yes. But others, so like a CNN is sort of fixed.
Do you have any advice on the number of layers that you should use? 6?
Yeah, keep going until your out of sample accuracy degrades. There's no right answer really. And deep learning is a field you need to be apprenticed into by like really studying with like someone that has done this a lot. There's like, you need to build intuition about it, but there's no mathematical proof. How do we split the training and cross-validation sets? How did we fix the size of what? The size of the article? Oh, good question. So we just, we featurized the headline and summary. We took the longest one possible, which was 52 words. That's a very long headline summary. And then for everything else, we just did like the first 30 and then we filled the rest with zeros, null words. And that's a common technique. Yeah. Same answer. It was, how long did it take to train? Oh, that's a good question. So for our static, so the first pass models, we did a static data set that was collected over November 2017. But we launched a system shortly thereafter that dynamically collects data and dynamically retrains. So now we're up to like 7 months of data, 6-7 months. And that's selecting more every day. Yeah.
The
Yeah, no, that's a great question. I mean, we should be doing image modeling. I'm a text person, so like the first pass was text, but eventually this project will be doing image modeling. But as in terms of whether we chose different images per a single article, we just chose whatever image that editors tagged to that article, which of course has an emotional effect, and I agree with you. We wanted to make the task as simple as possible, though. That's a great question. So we considered the history of worker responses when we were cutting out spammers. So if we saw that someone consistently disagreed with everyone else, we assumed that they were a spammer, and we cut them out. That was the only context. But you totally can look at that. You can look at like whether someone is just more likely to respond like with anger or sadness, or like they're like really sentimental like me. That totally has an effect, and that would be some hierarchical modeling that we will totally look at in the future. Yeah. Yeah. Yes. Yes. Bag of words for both of those. For neural nets, it was more of a sequence thing. Yeah. So it was a different encoding. So is there a repetition effect? Yeah. That's a great question, and I think that goes to your question about user modeling. It's a different approach, sure, but I think that that is that's not on my list to study right now, because I feel like that requires a lot more data. You need to, now suddenly an article is not just an independent data point, but it's a data point that's dependent on the number of trials that worker did. So suddenly, like, yeah, I mean, maybe we'll look at that when we have a lot more data, but I don't think we're in the state to look at that right now. What's it called? Fifth LAM? Like deep learning, transfer learning. No, I'll totally, what is it? Is it a text model or?
Yeah, it's a transfer learning.
I'll check it out. I mean, the pre-trained vectors that we used were glove vectors. So this model used Stanford glove embeddings. There's a lot of other embeddings that we could use, like doc2vec or whatever. But we found that glove worked pretty well. Okay, I'm going to move on to the results. So first thing you want to do is offline test. You do this by holding out a CV set. On our cross-validation testing sets, we found that 4 of our models produced greater than 70% AUC, and one of them was in striking distance. And that's, as they say, that's good enough for advertising. That is off the record. But that's sort of like, yeah, so we sort of had confidence in this. We're going to look at boredom and hope and interest, and we're going to see if there's ways that we can improve this. But this sort of makes sense because interest is sort of difficult to assess because something can be interesting for a lot of different reasons. So it's probably one that we need more data in order to understand. Here are the highest performing models. I don't have much insight into why gradient boosting performed better for hope, while like a pre-trained CNN performed better for hate. But at the end of the day, the system that we constructed is taking the max model for each emotion and it is scoring with just that model. So we have this mixture, sort of like an ensemble. We have this mixture that's feeding into all of our emotions. Using our models, we can spot check the ones that are most boring or the most fearful or happy or whatever. This fits with what we were seeing about sports. So sports and video games are the most boring articles. Love was a lot of wedding articles. So here we get a sense of polarization. So like this local tax article, probably if you live in New York or California, it doesn't cause hate. But if you live in the Midwest, might. Hope. I personally don't want to see the healthcare law fail, but maybe for a lot of people, this does cause hope. So we get this sense of polarization. We can look at individual articles and we can look at their emotion distribution. So for this article about being a bridesmaid, of course it causes a lot of love. But, you know, if you're like me and you're young and you're male, of course it'll also cause a bit of fear. And maybe some boredom as well. This is an article about driving a car in Manhattan. And if you're like me and you live in New York City and cars scare you, so it's going to cause a lot of fear as well. However, this is about congestion pricing. So you can see that it also causes a lot of hope and interest. And then we also ran an online experiment. We ran this ad against all of the different emotion categories. And we saw, we were looking to see if there's different types of articles, like a happy article or an optimistic article that lead to different behaviors of users. So we wanted to see if users would interact with this ad if it came on a hope article. Perhaps not surprisingly. So these are significance charts. So what this shows is a pair of emotions and whether it was significantly different or not. So, you know, is boredom significantly different from baseline? Yes, it is. Is love significantly different from boredom? Yes. So this is good. This shows us that this is baseline on the bottom. Nearly all emotions outperformed baseline significantly. And that was a positive result. Also, love significantly outperformed the rest of the emotions, which is interesting because we can see this sort of spread among emotions as well. And at lower confidence levels, it was even bigger. But this was a positive result, and it's allowing us now to go forward and sell ad campaigns against different emotion targets. And any questions about the results? Yeah. Was boredom also likely to be categorized as another emotion as well? Yeah. So we haven't looked at what the model scores different emotions yet. That will totally play into a polarization classifier that we look to build soon, which is if a model scores highly into opposing emotions, then it's probably a polarizing article. We also, I think what your question is getting at is that are there proxy emotions that might get us closer to boredom? That is not something we looked at, and that's also something that probably a neural network or something would capture to begin with. So it probably is not worthwhile looking at least in the near term. Okay, so I'm going to go quickly through this because I'm not sure how much time I have left. But the idea with any machine learning model, or at least in this context, is we have this stream of incoming events. So we have articles that are being published, and we want to take each of these articles, pass them through our different models to score them, and then we want to save those scores into some sort of database. So our model wakes up every 15 minutes. It's on a cron job. And it wakes up every 15 minutes. It scores the articles that came in during this past 15 minutes, and it passes them into this data store, Google data store. And then when the client comes in, the client can call this data store and get the scores. This is our architecture diagram told only through logos. Over here we have our CI layer. So our code lives in GitHub. Our model serialized. We have these static files right now, static model. So they live in Git LFS, and those are big files. Drone is the coordinator that we use to take our code and deploy it. There's a lot of open source New York Times drone packages that I encourage you guys to check out that'll coordinate drone deployments to Google GKE or GAE. So this is where our code and our models live. Drone takes any updates and it passes it through Docker and Google Container Registry into Kubernetes. The idea of using Kubernetes as a deployment manager, as a container manager was explored by Mark Whitfield on our team, who is really, really smart. And it's a really cool idea because if you guys aren't super familiar with Kubernetes or orchestration manager, Kubernetes is used a lot in web applications where you have a surge of traffic and you need to scale up the resources that you have available to handle that traffic, or maybe one of your resources goes down and you need to bring up another computer. Kubernetes makes sure that all of that gets handled so that your DevOps person can actually sleep at night. The idea of using this in machine learning, I think, is rather new, although places like Uber are definitely exploring that. But what this does, which is really cool, is that so we put our model files into Docker containers. And Kubernetes takes this Docker image, and if we have a surge of articles, we have a surge of traffic or something, it'll just scale up the number of images we have available to do scoring. And so we don't even notice anything. So we have this huge surge, and our system is able to handle it. With machine learning images, oftentimes the box can go down for unexplained reasons. Kubernetes just makes sure that we can sleep at night. And if a box goes down, Kubernetes will just bring up another one. And it's really great. It's a really resilient, robust system that we have. So this is managed by Airflow, which is basically a glorified cron manager in this context. So this is the core. This wakes up every 15 minutes and scores our articles and then passes this into Google storage. And our clients access it through a Flask front end, which is also managed by Kubernetes, but is not nearly as intense. The New York Times recently moved all of our platforms onto GCS, or most of our platforms onto GCS, and this was a really great thing for us because it helped us leverage stuff going on at Google, which is really great and innovative. And if your companies are looking at GCS, I think it's a great move. But I was not paid to say that. What we want to do in the future, though, we want to have our architecture to be dynamic. So the question over here about what are the time range of articles that we score under is a very good question because events can change, topics can change. North Korea might cause fear in November, but maybe a lot changes, and then eventually North Korea causes hope or happiness. We want our reality to reflect that, and we want our models to be training on dynamic data. So the system that we need to move towards is one that will use Airflow or cron job basically to do continuous active sampling. So this is Erlenmeyer. This is sort of an internal product that we use to train and manage our models. But we want to, every day, we want to actively sample new articles that we think are difficult. We want to upload those to Mechanical Turk. And we want to pull the articles that we have and train a new model every day to push that new model through Container Registry into Kubernetes. And so we can then do our normal pipeline, but now with an updating model. So we can adapt to a changing world. We're no longer stuck in like this static data set past. So that's pretty exciting. And it's launching, it launched this week, and we have to look at the bugs and stuff, but I'm leaving on Thursday, so I hope that it's in good hands. Thank you for coming and bearing with me. I'll take questions in a second, but feel free to reach out if I don't get to all of your questions. Those are my email addresses. Please reach out unless you're a recruiter, because I'm not going to be a good person to talk to in that regard. But if you're interested in working at the New York Times, as I said, I am leaving, so there is job openings, and please send me your resume or come talk to me afterwards and get my business card. So.